Okay, so to begin with, last time we were talking about enolate alkylation, and what that means is you make an enolate, and then you do an SN2 reaction to put, yeah, I did that during the first hour too. This is a fun day. There we go. We good? I pressed record. We're good. Sorry. Enolate alkylation, which is you make an enolate and then you do the SN2 reaction, right? And we said that we're going to pretend like this works excellently, uh, even though we were concerned about the possibility for our base to react with our alkyl halide. And the reason for this is that we only make a very small amount of enolate at any given time because of the because the pKa of this alpha proton is like 20, whereas the pKa of the conjugate acid of our base is around 16. So we only make a very small amount of enolate at any given time, which means if we add one equivalent of one molecule or 1 mole of sodium methoxide for every mole of our ketone, we're going to have at any given time a bunch of unreacted base. And of course, back in 351, you used that ethoxide as a nucleophile to do the Williamson ether synthesis, where nucleophile attacks electrophile and you make an oxygen carbon bond instead of the carbon-carbon bond we wanted to make. So we are worried about that. Nevertheless, we're going to pretend like we live in a world where that works out okay. And probably it does if you add this alkyl halide sort of dropwise very slowly. It's probable that the enolate is more reactive than the ethoxide base. And so if you add this slowly, it will react with what enolate is there, and then the base will make more enolate. And that's probably how you get this to work. But it doesn't work all the time. Nevertheless, we're going to pretend it does. Suppose we wanted to get a multiply alkylated product where we were able to install multiple alkyl groups on that alpha carbon. Well, what could we do? Well, we would probably try to use the same conditions to make the more substituted enolate, which would look like this, and then do the alkylation reaction. Nevertheless, this step here, sometimes the selectivity is not good. And that's just something that we observe in the lab. I told you before that when we're using reversible enolate formation, we're just going to show the product as the one that comes from the more substituted enolate. Nevertheless, there is the possibility for this undesired byproduct that you would get from the less substituted enolate. And so even though we're doing chemistry on paper, and I will continue to let you do this in a synthesis, in practice, it's only just sort of okay. Yeah?
Okay, why does this happen though? Because I thought the whole point of using using ethoxide, I thought the whole point was that you knew you were going to get the more substituted product.
That's right. The whole point of using ethoxide meant that you were going to get the more substituted product. That's true. Remember though that in our energy diagram, the selectivity has to do with the difference in energy between more substituted enolate and less substituted enolate. And there may be cases where that energy difference is small enough that you get product ratios that are closer to 50-50 than 90-10 or something like that. So sort of case-by-case basis, you may need an alternative. And so your text presents a couple of workarounds for trying to install two alkyl groups. And these workarounds are great. Though in a class where you're not actually in the lab doing the chemistry, I sort of question why we're spending time on these workarounds. And the answer is it allows us to introduce a new concept that's useful in biology. And that concept is called decarboxylation. So what I'm going to show you now is synthetically useful and practical, but a major take home that you should get from it is this new thing that can happen, a dramatic change in the structure of organic molecules that biology uses all the time. Okay, so we're going to make this molecule via a method that will work pretty much all of the time. So we're going to start with something that doesn't look even remotely like our desired product. This molecule is a beta keto ester. It's also called acetoacetic ester, or you can call it acetoacetate. Incidentally, synthesis of steroid hormones and cholesterol begins with a biological intermediate that looks pretty much just like this. It is an acetoacetate, but the identity of the group here is a little bit different. It's a thioester instead of an ester. So you'll see this kind of group before. Just a word of what your text says about what we're going to do here. Your text calls it the acetoacetic ester synthesis, which is fine, but that makes it sound like we're actually making this thing, which we're not. We're using it as starting material. So they're saying acetoacetic ester synthesis instead of synthesis of a alpha-alpha dialkylated carbonyl compound starting with acetoacetic ester, which I guess is more succinct. We're just going to call it enolate alkylation using a beta keto ester where the pKa of this proton that's alpha to both carbonyls is around 13. So if we use sodium ethoxide as our base, we're going to get 100% yield of the enolate, 100% yield of the desired enolate. The other alpha proton doesn't even compete because its pKa is so much higher owing to the fact that it's only alpha to 1 carbonyl. All right, and if you compare the pKa's of the conjugate acid of our base over here, 16 versus 13, we favor products by about 1,000 to 1. All right, so we can basically get 100% yield of this desired enolate. Something that somebody brought up during the first hour was, well, can't the ethoxide base act as a nucleophile to attack the carbonyl carbon? Isn't a negatively charged oxygen strong enough to attack to give you a tetrahedral intermediate? And I say, sure, that happens, but who cares? Because as soon as you get there, notice you have two of the same thing. It doesn't matter which one gets kicked off. You can attack and substitute till you're bored of doing it and nothing happens, right? So any attack on the carbonyl oxygen will go back to the starting material. But incidentally, that is why we try to match the identity of our base with the identity of the group on the ester, just so that that substitution process that's going on in the background is silent and undetectable. All right? So we make 100% of our enolate. This solves the problem, by the way, of the potential for whatever base is remaining to react in an SN2 fashion with your alkyl halide. So we've solved that problem. Now we've got 100% of the enolate. We can bring in a second step, our alkyl halide, and it will do the SN2 reaction whereby the leaving group leaves, and that will install the alkyl group on the alpha carbon. Now, if we wanted to make that product, we could stop there. Of course, we're not quite done yet. We're going to, in a third step, add another equivalent of base. That's going to make, again, an enolate, and we're going to remove the proton that's alpha to both carbonyls. Then we can bring in a second equivalent of our alkyl halide, or whatever alkyl halide we need to add. That will do the SN2 reaction to give us now the two methyl groups on our alpha carbon. All right. And just as a hint, notice that now we've made all of the key connections in our molecule, but somehow we have to get rid of the ester part. Okay, but the two carbon-carbon bonds we needed to make were here, and we've already done that. Okay, so the heavy lifting is now over because we've made the carbon-carbon bonds. Now we have to get rid of this ester group. Notice that our product here is still a beta keto ester, only it is now alpha-alpha di-substituted. That means there are two alkyl groups on the alpha carbon. All right, so what we're going to do now in our final step is we're going to add acid, water, and heat. And three things are going to happen. And we're not going to draw the mechanism of all of them because I don't want to, because you've seen many of them before, okay? So part A of this step 5 is we hydrolyze the ester. And that, if you want to review that, you need to go to your notes in chapter 16 under ester hydrolysis, or turn in the text to chapter 16, ester hydrolysis. Briefly, your acid will protonate the carbonyl oxygen of the ester such to generate a reactive oxonium ion that water can attack. You get a tetrahedral intermediate. You do proton transfer to trade who's the good leaving group. You end up kicking off ethanol, and that will give you the carboxylic acid. Okay. Notice now, because we've hydrolyzed the ester, what we have here is a beta keto acid. What happens next is going to see that most effectively, I'm going to redraw the beta keto acid in a conformation that will help us get to the desired product a little bit more clearly. Notice that if we rotate around this carbon-carbon bond, we can make a hydrogen bond between the carbonyl oxygen and the proton of our acid. And it's a 6-membered ring. The bond angles all work out nicely. So the acid group can hydrogen bond with the beta keto group. Now, what we're going to do next is step B, which is called decarboxylation. I'm going to show it to you stepwise so you can get it down conceptually. Your book will show you all these arrows happening at once, and in the end I will too, but I want you to be able to think through this because having 4 or 5 arrows at once is sometimes a little bit much. So think of it this way. Imagine that lone pairs on the oxygen that were previously hydrogen bonding with this proton, remove it completely. That would generate an oxonium ion here and a negatively charged oxygen there. Okay? Now, we're going to think of this group in orange as being analogous to a tetrahedral intermediate where you have some nucleophile and some leaving group, and electrons can kick down and kick off a leaving group. Right? We saw that a whole lot during our previous unit. The stuff in purple is a good leaving group. That may not become apparent, but after we're going to draw it after it leaves, and it should become clearer. We're going to have electrons on this oxygen kick down and kick off the leaving group, and the electrons in this bond are going to end up on that alpha carbon. All right? When that happens, let's draw the product. The purple portion of our molecule is going to look like this. Here's the alpha carbon, but notice that it has a resonance structure that looks like this. In other words, that purple thing, the leaving group, the reason it's a good leaving group is it can leave as the neutral enol. Okay? And enol because we have a double bond between carbonyl carbon and alpha carbon, and then what used to be the carbonyl oxygen is an OH group. And then, oops. So that was what left. And the thing that did the kicking off is CO2, which is a gas and bubbles off. So this decarboxylation step is irreversible. You make the CO2 and it's gone. All right? So I've shown this to you stepwise. What you, in reality, it's most likely concerted. And I'll allow you to draw the mechanism either stepwise or concerted. I don't care. But what your text will show is lone pair electrons on the oxygen attack the proton. These electrons kick down to kick off the leaving group to form the enol all at once. So you're welcome to do it any way you want, and if you want, you're welcome to do it either of these two ways. I suppose not any way you want, right? Check and convince yourself that the arrows that we're showing here lead to the enol. Okay, so that's part B, but we're still not at our desired ketone product. Fortunately, we've made this enol. We've made this enol, and part C is tautomerization. We're going to tautomerize from enol to keto form. This is downhill in energy because carbon-carbon pi bonds are not as strong as carbon-oxygen pi bonds. The word tautomer is a kind of isomer. Tautomers differ in only two things: the location of a pi bond and of a proton. Notice that before we have a pi bond here and a proton here. Ew, red on purple is kind of weird, isn't it? Whatever. And now we have the proton here and the pi bond there. That's what we mean when we say tautomerize. We're moving the position of a double bond and a proton. What tautomerization looks like in terms of mechanism is simply you have some base, and it doesn't matter what it is, because the keto form is downhill in energy. Even water is probably good enough to do this. You make the enolate again, which of course has a resonance structure where you could put the negative charge on the alpha carbon, and then you simply reprotonate, probably with the conjugate acid of whatever base you used, reprotonate on the alpha carbon, and that gives you your ketone form. Okay, whenever somebody writes tautomerization, that's the process. Okay, all right, so this last step is the one that's most involved: ester hydrolysis, decarboxylation, and that's the new thing, and then tautomerizing from enol to keto form, and that's a review of stuff from 351. Okay, what questions do you have about this process? Yes?
I just want to ask a question about when it says sometimes selectivity is not good. I
Yeah.
just want to make sure I understood that. Is that because the energy levels of both possibilities are really close?
Yeah, the ability to make selectively one desired product versus the other depends on the difference in energy between these two enolates. And if that difference in energy is small, your selectivity shouldn't be good. Yeah. Okay, others? Okay. So I want you to look at our product because now we're going to think about how to use this type of reaction in a synthesis. And I want you to look at the pattern and what is in our starting material versus what ends up in the product, okay? So I just want to summarize the reaction. We did mechanism there. I'm going to rewrite the steps of the reaction real quickly here. We first add a base. We then add the alkyl halide. We then add another base. We then add another alkyl halide. We wouldn't have to add another alkyl halide. That's the desired product we want to get this time, so that's why we're doing it. And then finally, we do the trifecta here: acid catalyzed ester hydrolysis, decarboxylation, and tautomerization to get the ketone. Notice that the methyl group in the starting material ends up in the product. The carbonyl carbon and oxygen and the methyl group in the product come from this portion of our starting material. Notice that in this reaction we're going to break the bond between the ester carbon and the carbonyl carbon. And then notice that our alkyl groups come from these alkyl halides. I think I screwed up in where I drew that line. Sorry. Let's be clear. The carbonyl carbon of our beta keto ester, the methyl group, the oxygen, and also the alpha carbon all end up in the product. The two new things we're introducing are these methyl groups. And then what happens over here? Well, ethanol gets kicked off as a leaving group, and then we also lose CO2. So that's where everything's ending up. But when you see a ketone, particularly a methyl ketone is a ketone where one of the two things attached to the carbonyl carbon is a methyl group. You could have made that from this beta keto ester, all right, via that process of sequential deprotonation and alkylation followed by ester hydrolysis, decarboxylation, and tautomerization. All right, so let's try to think backwards now. I'm going to draw for you a product, and you have to make it from this starting material plus whatever alkyl halide you want. Now you'll notice in the product there is a ring. And I did that deliberately because I know that rings scare you. I know that when you get in the testing center and you see a ring, you're tempted to go into DEFCON 5 or whatever it is, where if you've ever seen, I don't know, I'm not a big watcher of SpongeBob SquarePants, but my sister was, and she showed me this clip where somebody asked SpongeBob a question, and then it zooms into his brain, and there's lots of mini SpongeBobs running around, flipping through filing cabinets desperately, throwing things here and there, and everything's on fire. And that, I think, is what happens to you when you see a ring on a test. It's just sort of alarms. And so you got to make the ring. Now let's actually take a deep breath and look at what we've done before and look at the similarities between the molecule we made before and this molecule. All you have to do is have some other stuff here, and then it's the same thing. In other words, are you able to put on the fire extinguishers and let things calm down to realize that this is simply an alpha-alpha disubstituted methyl ketone. And if we're thinking retrosynthetically like we did up here, we could see that, okay, this carbon and this one are going to come from the starting material. These are the two new carbon-carbon bonds I had to make, and these are the carbons that are going to need to be on alkyl halides. The only difference is up here, they were on different, they weren't connected to each other. Here they're going to have to be. So let's see if we can use this sequence to get from starting material to product. Let's think backwards. If the last step of a reaction that gives you an alpha-alpha disubstituted methyl ketone is this hydrolysis of an ester, decarboxylation, and tautomerization, let's think about what it would have looked like before tautomerization, decarboxylation, and ester hydrolysis. Notice before, the thing that preceded all of that was this beta-keto ester. So, what would that look like? Well, probably then that looks like this, with a 6-membered ring there. All right. Here's the carbons that end up in our product. Here are the two for the bonds we have to make. And then here is that portion that gets kicked off in the ester hydrolysis and decarboxylation. Okay, did you see that jump? Okay, now that jump is easy to see when we're all here together and I'm drawing it on the board, but it's going to be hard for you to remember under the high pressure testing environment when you see a methyl ketone to think, that could have come from a molecule where that alpha proton wasn't there and instead in its place was this ester. Okay? And if you're struggling with this, it might be a good idea for you to at least draw the decarboxylation mechanism to show how you get rid of this ethyl group. You don't have to draw ester hydrolysis because that's chapter 16, but it might be useful for you to draw the decarboxylation mechanism and then the subsequent tautomerization so you can convince yourself that once this is gone, this product is what you had. Now, okay, how do I get from that beta-keto ester intermediate to the starting material with no alkyl groups? What would I have had to do? What do you think my alkyl halide needs to be? Go ahead.
I'm not sure if you do this, but could you just make one long carbon chain with an alpha halide on each end?
Okay, a carbon chain, how many carbons am I going to need?
1, 2, 4. Or would it be 3?
1, 2, 3, 4, 5. The alpha carbon comes from the beta-keto ester. Everything else has to come from our alkyl halide. So yeah, I need a 5-carbon chain, 1, 2, 3, 4, 5. All right, so what's that going to look like? We would first, to do that, let's see, we would first take this beta-keto ester, we would add the base to make 100% of our enolate. Then we would bring in this alkyl halide, and we would do the first SN2 reaction. And that would get us to the monoalkylated product. 1, 2, 3, 4, 5. So at this stage, I'm going to label the various parts of our molecule. And then all we have to do is, in a third step, add base. That will remove the proton from the carbon that's alpha to both carbonyls to make our enolate. 1, 2, 3, 4, 5. Here's the enolate, and then it will be very fast to do the intramolecular SN2 reaction. The reason intramolecular reactions are fast is that the two reactive partners, nucleophile and electrophile, are, by virtue of being in the same molecule, already close together. They don't have to swim around to find each other. And that makes the desired beta-keto ester. All right. Sorry about penmanship. All right. Questions? Yeah.
So for the sodium, the ethoxide, right?
Yeah.
I'm assuming that would attack the bromine, like the long chain bromine at the end there. Would that ever do an SN2 on it and not have, but because it's intramolecular?
Good. Good. Yeah. The question is, do I worry about, and I suppose you could ask about it here as well. Well, no, let's deal with the question at hand. Do you worry about the potential for sodium ethoxide, the ethoxide base, when it sees this starting material, instead of removing the alpha proton, could it also compete and do an SN2 reaction? And I think it's very reasonable to be worried about it. I would be worried about that too. I think the fact that this alpha proton has a pKa of 13 and is very acidic, coupled with the fact that protons are smaller than carbons, and I think it's probably faster for this ethoxide to remove this proton than to attack the carbon. Once you've got the enolate, that happens quantitatively. There's no more ethoxide present, and then the intramolecular one is fast. Somebody during the first hour asked, okay, well, if protons are faster to remove, why not remove this one via an E2 reaction? And the answer to that is likely that protons that are beta to leaving groups can do E2 reactions. They can be removed, but their pKa's are generally much higher than 13. So the most reactive part of this molecule is this proton, and that's what reacts first. And that's probably why we don't see any of the competing possibilities, just removal of that proton. Okay, good. What else? Okay. Looks good when I do it. Can you do it? Go ahead.
You were also going to mention, I'm assuming earlier, where if you were to attack like the alpha halide with the ethoxide, would that be a problem in it, or would you do something?
Right, up here, and the reason it's not a problem here is because we're only using, for every 1 mole of this, we're only using 1 mole of this. Another way of saying that is we're just using one equivalent of base, and it reacts because the pKa of this proton is 13. That reacts 100%, and we do that before we even show the alkyl halide to the molecule. So at this stage, this alkyl halide never even sees the sodium ethoxide. Yeah. Yep. What else? Low battery, 5% remaining. Joke's on you, because we know that 5% we can stretch for like 40 minutes. Okay. So we can use this method. Go ahead.
So once you have that alpha halide attached once, what stops it from reacting with a different
Uh-huh.
instead of doing the intra? I get that the intermolecular is going to be faster,
Uh-huh.
but it could potentially also cause intermolecular.
Right. Great question. So at the stage where we do the intramolecular reaction, I think the question is, how likely is it for one of these enolates to react with the other alkyl halide? Is this sort of what you're asking about? Yeah, I think the thing that I think the thing that saves you from that is the fact that when we add the base, it completely removes the proton. So it's not like this enolate is swimming around at the same time with this molecule, right, which has the alpha proton. If there were a large amount of this present, then I think what you're talking about might be a possibility, but the fact is there's none of this because we completely, with one equivalent of the base, we completely remove that proton. And once all of your beta keto ester is present in enolate form, the intramolecular reaction is going to be orders of magnitude faster than finding another. This is a problem in organic chemistry, though, because depending on the size of the ring between the size of the tether between nucleophile and electrophile, it can start to get slower. The longer the tether, the slower it is to bring the two ends together. And then you do start to see some competing, I suppose, dimerization instead of intramolecular cyclization. And you can sometimes prevent that by using a lower concentration. So you just dilute things so that the likelihood of two molecules finding each other is smaller. Yeah. All right, what else? Okay. Your overconfidence will be your undoing. No, so sorry. Your faith in your friends is yours. Sorry, I'm always thinking about Star Wars. Just can't stop. Okay, so make this. Go ahead.
Sorry, just going back to the last one. This just thought with resonance,
Uh-huh.
would it be possible to do like an ether synthesis using the oxygen at the top there?
Okay, right. Would it be possible instead of by resonance, I think your point is that this negative charge is on multiple carbon, or is on that carbon on those two oxygens. And the question is, do we ever alkylate on the oxygen? You can do that, but most of the time not, because this charge on the alpha carbon is actually the electrons represented by that lone pair are in a molecular orbital that's on this oxygen, and that alpha carbon. But there's a bigger amount of that orbital. It's called a higher orbital coefficient on the alpha carbon. So the alpha carbon's just more reactive. Yeah. Okay. So let's make that. We got another ring. And this is no longer a methyl ketone. Huh. What are we going to do there? If we wanted a methyl ketone, we would have started with this molecule, and we would have remembered that this portion of the molecule, the methyl group and the carbonyl and the alpha carbon, all end up in our product. But this we're going to have to introduce from somewhere else. We could see an analogous situation here, only what are we going to do about that OH group? What do you think? Go ahead.
Use TB, EMS, CLO, whatever it is.
So You're saying let's do something like that, but you don't want the proton to be there.
Right. So
Okay.
do the protective group, right?
All right, yeah, conceptually, if we step back, you might say, okay, let's just start with that acid. But your problem, you're exactly right, is that when you go to deprotonate the alpha carbon, you're just going to deprotonate the acid. So what do you do? What is the best way to protect the OH group of a carboxylic acid? You could conceivably use a silyl ether, but it turns out it's much easier just to use another ester. Whoa. Did that catch you by surprise? Why does that work? Well, first of all, that's great because now it's a symmetrical molecule. You no longer have to distinguish one from the other. And this is called diethyl malonate, or the Malonic Ester, and your book will call this the Malonic Ester synthesis, which again is a pain because it masks the difference, it masks the similarity between these two reactions. What we're going to do with that starting material is exactly the same as what we did before. We just have to make sure we get the right tether length. So deprotonate with a base that matches the ester groups on both sides. That generates your enolate irreversibly. Then, let's see, how many carbons do we need in our dialkyl chain? Just 4 because it's a 5-membered ring, right? So let's bring in the 4-membered, the 4-carbon 1, 2, 3, 4 alkyl halide. That's going to make the monoalkylated diester 1, 2, 3, 4. Feel free to bring highlighters in on the exam if this kind of thing is helpful to you. That's the new bond that we made. Then we're going to add a second equivalent of base that will deprotonate our alpha carbon, removing the remaining proton that's there. 1, 2, 3, 4. Oh, why am I still showing that alpha proton? Once you're there, you've got the intramolecular SN2 reaction. Oops. And that will give us the alpha-alpha disubstituted diester. Now, how do we get from here to here? We're going to do the same thing we did above, right? We're going to use the acid conditions to do ester hydrolysis, decarboxylation, and tautomerization. So what would that look like? Ester hydrolysis. This is where your acid comes from because now you hydrolyze both esters to now get, instead of a beta diester, you get a beta diacid. Then we decarboxylate. We can do the decarboxylation reaction in exactly, how long were you going to let me leave that there? Okay. We can do a decarboxylation on a beta diacid in the same way we can do it on a beta keto acid. The key is that there is a carbonyl that's beta to one of the acids. So we can draw this happening. I'm going to draw it all at once. Remove the proton, kick down, kick off the leaving group, make the enol. That enol would look like this. We lose CO2. There's our enol. And then we can tautomerize using the same approach that we used last time, remove a proton from one of those oxygens and then protonate on the alpha carbon, and that gets us to our desired product. All right, so the pattern here is if you have an alpha, and that's kind of, I'm sorry, needed to keep this smaller so it could be all on one screen. That's maybe okay. The pattern here is an alpha-alpha disubstituted carboxylic acid. When you see that, you need to think, I could have made that starting with the beta diester. And see that that's not a different reaction than we did before when making the methyl ketone, right? We used basically the same steps, same chemistry. The only difference was in the starting material. So please don't think of these two reactions as separate. They're the same thing. Yeah?
I'm just trying to get the names down. Why is that one called beta diester?
Why is it called a beta diester?
Yeah.
Well, if you pick one of the esters and call it the carbonyl carbon, and this is the alpha carbon, that's the beta carbon. There's two esters and they're beta to each other.
Okay.
Yeah, so that's why it's beta diester. Okay, other questions? I mean, do you see the similarities? The reaction we did above, and I'm not going to write down all the steps because I've written down all those steps a lot, right? Leading to the methyl ketone versus a slightly different starting material, same chemistry, and let's just, well, we made a different size ring, and I'm scared that some of you are going to leave thinking, oh, well, if I want to make a 6-membered ring, I got to use the first one. If I want to make a 5-membered ring, I got to use the second one. That's not it at all. You control the ring size based on the size of your alkyl halide. So I'm just going to say that we could make the beta diacid, I'm sorry, we could make the alpha-alpha disubstituted acid and the corresponding alpha-alpha disubstituted ketone using similar methods. All right. In the last 2 minutes, we're going to introduce something else. I'm just kidding. Just go.